that said, let's hit it. So, and this is on page, I think it's 83 or something. No, 85, page 85. Yeah, 85. Okay. And let's start with 5.6. Okay. So the idea is we're going to start with this question. We've got a mass hanging there. And I want to start by doing the first two parts of this question. So you've got a mass, it's held up by a system of strings, and then each string is tied to this washer at the center that I'm circling in green. And then you're asked the first question is, under what circumstances does T3 equal mg? And then I want you to draw an FBD. So I'm going to talk to you after I get my FBD drawn. And then if you want to work ahead, remember that you've got the solutions, but maybe wait after you get done with part C before you go on. Do whatever you want. If you finish way ahead of me, keep working. That said, we're going to regroup after part B, then after C, and then we'll talk for D and E at length. And okay, so go ahead and get this one started while I get the board started too. I'm going to get this picture drawn, okay? And if it helps, let me check here. I think I used green for tension 1 and blue for tension 2. So if you're color coding your work, I'm going to use green for the left rope and blue for the right rope or string. Let me get that back on screen for you again. Whoops, forgot to hit the button. I'm sorry. Thought I hit the button. There it is. Remember that there's a difference between theta and phi. Okay. There we go. So here's the problem I've drawn up. Okay, so we were shown tension 1 here in green, tension 2 there in blue, and tension 3. And part A immediately asks us, hey, under what circumstances will T3 equal mg? Do you guys remember from last time what has to be true for that tension to equal the weight? And I'll give you a hint. Here's that weight that's hanging down there. And then there was a tension pulling up on it, tension 3, right? Obviously, there's mg downwards. Under what circumstances does tension 3 magnitude equal mg?
When acceleration is 0?
That's right. So that's what I want you thinking about there. So if acceleration is 0, which if you hang something from the ceiling, typically your whole house or apartment is not moving, or, you know, the ceiling of, yeah. So, you know, obviously if you were in an airplane or a car or something else or an RV or something, maybe there you could have something complicated, or an elevator, right? That's the one that I was thinking of. If you're in an elevator, this might not be true. That said, okay, cool. So if A equals 0, this is T3 or mg interchangeably. We're going to assume that's true. So now you could argue this is the FBD, and maybe I'll throw in one more piece of information. I'm going to assume we're using a standard coordinate system, and we're assuming that acceleration is equal to 0 if you hang something and it doesn't tell you otherwise. All right. So in this case, I need to split up this tension 2 into components. I need to split up tension 3 into components. So the question becomes, which angle, sine, and cosine? So last time everything was in a line. Now we got to think about angles. So in this case, if this is phi, one of these two angles is also phi. Is it the upper or the lower? Is this phi the upper angle, or is the lower angle phi?
Is it the lower?
Mm-hmm. Look at this. Parallel lines, right? So alternate whatevers. That's my technical geometry proof there. Alternate whatevers, you know. Whatever. This is phi. Let's do the same thing over here on this one. So somebody other than Esteban, which of these two angles? Is it the left angle or the right angle? Which one is theta? Is it the left or the right? Somebody other than Esteban.
The left?
Let's see. So the left would be this one. And let me show you, if I show you this, look at these two parallel lines. Based on that, this one would be theta. I don't know if you can see that. Does that make sense?
Yeah.
And look at it. You can kind of see this triangle if you bring it over. Here's another trick. Notice that I have tried deliberately not to draw angles near 45 degrees. Doesn't this angle look bigger than 45? So does this one. That's really what I'm doing in my brain, right? So by doing a good job drawing pictures and avoiding 45-degree angles in your pictures, it can be easier to tell. All right. And so now I'm saying these two lines are parallel. Now, if you wanted to, you could say, oh, well, this is theta by vertex angles, etc. So notice that there's a lot of geometry in physics. All right. So now somebody help me out. I think that was Esteban and Jake. So let's see if we can get somebody else involved here. This side, this component, I need to figure out this side. Is it going to be T2 cosine or T2 sine of theta? So I want the X component here. What do you think? Somebody other than Jake or Esteban. And you could throw it in the chat if you want to. And again, if this is too slow, work ahead. Use the solution.
T2 sine.
Excellent. And that's what I was trying to trick you. We normally think X always gets cosine, but in this case, sometimes in physics problems, angles are drawn to a vertical axis. When that happens, the traditional sine and cosine get flipped. The other one would obviously be the other one. So adjacent gets cosine, opposite gets sine. Excellent. And so over here, this one is traditional. This is theta, or sorry, this is phi. So this is T1 cosine of phi because it's adjacent. All right. So we could see here that if you can't get this step done right on a routine basis, you'll never get the equations right. So you'll never get the algebra right. And then you'll never get the answers right. So that's why I'm spending some time on getting the angles right. And you can see that there's a number of weird geometry rules we could use. Okay. Now that we've got this, I'm going to lower this down just a little bit. Let's go ahead and write the sum of forces equations. If you recall, Give me a second. So we know that sum of forces in the x direction, this means all the arrows that are going left or right. So this side of the equation is all the left-right arrows, whereas this is just, in this case, it's going to be 0. So similarly, this would be all the arrows up or down from this picture. So go ahead, take a second and write down what you think it should be, and then we'll work it out. So I'm going to go ahead and write it down too. Be careful with theta versus phi. Phi has that vertical line. Theta has that horizontal line. It's not vertical, it's nearly vertical for. So get your angles right, your trig functions right, your plus minus signs right. Okay. That's what I ended up getting. So here's the x equation right to here. Let's get rid of some of this junk. And here's the y equation right to here. Again, the sum of forces in the x was associated with the arrows, and hopefully you can read that. Let me get it even closer here. So notice T1 cosine has a left arrowhead. That's why it's got the minus. It's a cosine, and it's a phi. T2 sine theta positive x. That's why it's positive. Going over to the y, these two, the red and the blue, are both positive. This one is sine of phi, cosine of theta for that one. And then you could have said T3 or mg here for this special case where a is equal to 0. And hopefully that makes some sense. All right. I'm going to pause and go to gallery view here. Any questions on any of that part? I'm going to go a little slow on this just because, like I said, if you can't get this part right consistently, you're going to have a lot of trouble. I'm going to assume you're doing, remember, you could also chat with Memo too if you don't want to talk to me or whatever. Okay. Whoops. So let's go back and look at what we've done and see how far we got in the problem. We did this, we did this, we did this. So now look, we want to solve for theta by eliminating T2 or vice versa. Eliminate theta and solve for T2. So the idea here is we are going to assume this blue force and angle are unknown. And part D is figure out the angle. Part E is figure out the force itself. Okay. Now, you could look at the solution and just kind of play with it, but maybe let's talk about this and see if I want to. Okay, so again, everything in here is known except for the blue piece in each equation. So notice there's two things you don't know, T2 and theta, T2 and theta. So we're going to try and say, okay, if everything else is known, can I get both T2 and theta? What strategy would you try? Let's say we're trying to get theta. You know what? This question's always goofy. Oh, go ahead. Try. Give it a shot and realize the question's goofy, so it's okay if it didn't make sense. Give it a shot.
Yeah, well, so I guess my first try would be set them equal to each other and then try and get the ones with T2 on one side and like factor out the T2 or something. And then maybe we can use an identity or something.
Okay, that's a really cool idea. It probably is not the easiest way. So, and rather than try and like, yeah, there's so many different things you could try, and that's one of them. Another one that's common is somebody might say, well, if I want to get theta, why don't I solve this equation for T2 and then plug that into here? And that would also work, but it's also not the fastest way. So there's a cool trick that I wanted to show you. So what I would do, so just so I have some room to work here, I gotta, whoops. All right, whatever. We'll go right to there. What I would do is I would get this side and solve for T2 sine theta equals some stuff. And then immediately below it, I'd write T2 cosine theta equals some stuff. Now, in this case, before we get ahead of ourselves, let's do that. T2 sine theta would be equal to, bring that over to the other side, it becomes positive. This would be positive T1 cosine of phi. T2 cosine theta, if I leave this here, bringing this over, mg becomes positive, T1 becomes negative. And remember, Jake was mentioning, could we use an identity maybe or something? And that's exactly the trick I was going to show you. At this point, I want you to ask yourself, what would Horatio do? If you were Horatio, you would take a ratio. That's, I don't know if that helps, but whatever. What does taking a ratio do? On this side, what gets canceled out?
T2.
What is sine theta divided by cosine theta?
Tangent theta.
And notice now to get the angle, it's really easy. All I have to do is solve the rest of this crap, plug in the numbers. Remember, known, 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 known. We'd stick in a bunch of numbers, take inverse tangent of it. We got the job done. So that is a cool trick. And I think it's easier than the other ones. What do you think, Jake? Do you think that's easier than what you were suggesting or not?
Yeah, because I mean, I haven't really worked out the way I was
same.
suggesting. I think it would end up kind of the same way.
I think it would.
Steps on my end, though.
Yeah, and it might have only been 1 or 2 extra steps. So you had a good idea. Great. All right. So let's see if I can get that there. All right. That was a good thought. All right. And okay, so now I want to work this another way. And then we'll go to the solutions and pick up anything else. Just a second. These tricks are so common, it's worth saying them a few times, all right? So that's why I'm doing this, is these tricks are going to be used in a huge number of problems. Let's say you had the same equations and you instead wanted to get rid of theta. Now, what you could do is what we just did. You could solve for theta, take that tan inverse. Now, think about it. Then you'd have to plug in that big mess into here. Whew. If you had numbers, it's not terrible, but if you had letters, it's really, really bad after a certain point. So there's another cool trick you could do with this. Square this. Now, whatever I do to this side, I have to do to the other side. So I'm going to square both sides. Now, think carefully. If I square this side, it becomes t squared sine squared. and t squared cosine squared. Okay. All right. Okay. So now what happens if I square these equations and add them together? The t2 squared can factor out. What's left on this, if I factor out the t squared, equals a bunch of other stuff. Now, obviously, the bunch of other stuff is really long. We'll get to that in the solutions. But this is the point. What's sine squared theta plus cosine squared theta always equal to?
1.
1. So this is equal to 1. It drops out, and it's actually really easy to solve for T2 now. You just take the square root of that other crap. And so those are two tricks. I just wanted to expose you to them because they get used. Yeah, right? Trig identities, man. Every once in a while, they come in handy. I guess usually in physics, right? So let's go take a look at the solutions and see if those solutions make some sense now. This one. So here we took a ratio, the t's drop out, and you get tangent theta, right? Equals this junk. And notice that's just worked right there. And then the one below, there it is. You factor out this. This junk in here goes to 1. Now, you could actually take some more effort and square these things out. And if you do that, you got to be careful here. I don't know if you could tell, but you're actually going to get T1 squared plus mg squared. But then you're going to have to also add in minus 2 mg T1 sine phi. The idea is when you FOIL this thing out, it looks a lot like the law of cosines because it basically is. But like you got this T1 cosine squared, you're going to get a T1 sine squared and an mg squared. These two terms combine to that, but you also have the cross term. The cross term gives you this, right? 2 times the first term times the second term. So you could try and FOIL it out and see if it gets simpler. And it is a little simpler, but it's still just an ugly mess. All right. So as a result, I was just like, well, why don't we just leave it at that? Because the angle is in there no matter what. All right. Let's see. Any questions on that part? Is that making some sense? That's angles. All right. Let's see here. Let's do, let's look at the next one. We'll just keep kind of plugging along here. And remember, if I'm going too fast, it's online. Just add some questions in the chat to slow me down or unmute, anything you want, okay? Whoops, I want to go to this one. So something that I have discovered, if I don't do question 5.7, even though it looks nearly identical, there's a bunch of mistakes that show up on test day. So we're going to look at 5.7. Now, to give you a visual on this one, I brought my handy dandy flask here. So I've got a rubber band on this thing. It's not a perfect example, but you could imagine here, if I just put this against, I don't know if you could see that well, but there. Now you can see the angles if it's up against my face. So the idea is this thing is hanging here, and we see that there's two different angles, but if I get this thing exactly centered, the angles basically are identical. So the angle by this finger over here and this finger over here are essentially identical if this mass is centered. Now, what force is holding this thing up? What's holding up this flask?
T1 and T2?
Yeah, the tension in the rubber band itself. So a common misconception is people are like, well, isn't the flask being held up by a normal force, right? And I could see how you would think that. It's just, if there was no tension in the rubber band, it wouldn't be held up. If it's holding that thing up, there is tension in the rubber band. I want you to think of a mass on a string as being held up by tension, not a normal force. So in terms of pictures here, let me show you what I mean. I don't know why, but unless we talk about this right now, I see this every time on exam 1. Well, or what? I guess the final exam, whatever. It's online mode. Everything's a little messed up. The idea is this. You have this mass. mg is pulling it down. There's some weight. Okay. Now the string is wrapped under here such that one side goes off here and one side goes off there. And we were told that this angle is phi and this angle here is phi. Same angle. We did this particular problem symmetrically to speed it up. Now, this you could say is tension. Let's just call it tension because it's the same rubber band. It's the same tension. So in this case, what students sometimes do is they'll be like, well, it's sitting on the rubber band. They'll draw a normal force like this. And that's not true. There is no normal force there, right? It's being held up by the tension in the rubber band. So if you account for that and try and account for it with a normal force, you end up double counting the forces or you don't know how to solve the problem. So think of it like this. And that's all I wanted to say about that. Well, let's do this. Hopefully you agree. If it's hanging there, if this thing's hanging here, what's the acceleration of it?
0.
0.
0. So I'm going to stick that in here. And what problem was this? Was this 5.7?
Yes.
Thanks. All right. And so we're going to assume if it's hanging there, the acceleration's 0. What should be true about this force component to the right and this force component to the left? Well, if the tension's the same and the angle's the same, hopefully you agree the left and the right components cancel out. So really all we need to do is figure out these vertical components. So my question to you, is it T cosine or T sine of phi? Let's get this angle inside here. Think, what's this angle? Is it phi or is it 90 minus phi?
So that would just be phi.
Exactly. This angle is 90 minus phi. That's sloppy. This angle down here is phi. Yeah, geometry. Oh, don't worry. You'll learn your geometry in this class for sure. So yeah. All right. So this side over here should be T sine of phi. You could also call it T cosine of 90 minus phi. Notice you see a trig identity. We immediately see that sine of phi is equal to cosine of 90 minus phi. Do you see that? So this is a common one that we'll talk about when we get to chapter 12 in Physics 161. That said, why wouldn't we just write it this way? So help me out. I need the sum of forces in the y direction should equal mass times acceleration in the y direction. This comes from the arrows. Give me some arrows, vertical. Just give me any one of them, somebody.
So we've got negative mg.
Negative mg. I like it. What's another one?
Positive t sine theta.
How many of those? How many?
Two.
Two of them. So are you okay if I write this? There's a t sine phi here and a t sine phi there, and they're the same because in this one, phi was the same angle. All right. Somebody else. All this should equal what?
0.
0, because why?
Because acceleration is 0.
Exactly. Not the mass. The acceleration is 0, right? So perfect. All right. So now I'm just going to rearrange this and solve this for t. See if you can get that. So solve this, everybody. T is equal to what? Flip it around. I'll leave it up on the screen so you can see. So solve this crap for t. Hopefully that's what you got. The tension is mg over 2 sine phi. Give me one way to check that answer. What's something we could check? Check the... How can you check any algebraic answer? We check the...
Oh, check the units.
Yeah. So this is a force. That's a unit of Newton. On this side, that's a kilogram. G has units of meters per second squared. What are the units of 2?
No units.
How about the units of a function?
No units.
No units. And wait a minute, a Newton is an mg. It's a kilogram meter per second squared. That's awesome. So a lot of times we're actually going to end up writing our forces algebraically, where it's the weight times some other crap that has no units. And this is a good way to write problems because they start to look similar then. All right, so the units check. What's another way we could check this result? Does anybody have any thoughts? Trying to think about this result. What are some common easy angles to plug into trig functions? One easy one is
0, 45, 90.
Yeah, let's start with the two extrema, 0 and 90. What would 0 degrees look like? What would the string look like?
Be flat out.
That's complicated. Let's try the other one. What would 90 degrees look like?
It'll just be one string. One tension up.
It'd be this, right? Another way you could view it is two strings pulling straight up. Do you agree? Is everybody cool with that? Basically, 2 strings pulling straight up. How much weight should be on each string?
Half.
Half. Let's see if that makes sense. If you plug in 90 degrees, what's sine of 90? It rhymes with none.
It's 1.
There you go. So mg over 2, this makes sense. Now let's think about it the other way. What if, okay, what's sine of 0 degrees?
0.
Sine of, yeah, so what's something divided by 0?
It's indeterminate. Undefined.
Infinite. Yeah. So that's not good. So let's think about it. That means that you start out when you're hanging this thing, the tension should be close to 50-50, same amount of tension on each rope, but also half the weight on each rope. As we stretch it, we expect, notice I'm having to put, I do not want this to snap in my face, so I'm going to stop right there. The idea is when I stretch it, there's more tension in the rope. I'm not just supporting the weight, I have to support extra tension left and right. So as we pull this thing tighter and tighter, the angle gets closer to 0 and the force in the string or the rubber band goes huge, right? And so this makes sense. If you go to a really, whoops, let me try and get this at the same. Sorry. What am I going the wrong way? There, I was going the wrong way, sorry. So now there's an extreme amount of tension on this, right? And so the tighter you put a clothesline, the less angle you get, the more tension you have in it. And then as you hang more and more mass on it, the more likely it is to break. So a clothesline, you usually want the clothes to not touch the ground, right? So if you're hanging a clothesline across, usually you want to put a lot of tension on it. But the issue comes, the more stuff you hang on it, the tension in a clothesline actually can get very, very large. That's why you don't just use a string. You use some kind of clothesline, which has got some kind of metal, probably a braided metal core with some nylon on the outside or something like that. But the idea is when you start putting clothes on it, there's a massive amount of tension on it. And that's why you don't just see like a tiny little stick holding up a clothesline. You need a lot of, the support cables at the end will cause an extreme amount of force on whatever you hang it on. So you need to be careful and make sure those supports can withstand that massive tension of hanging sweatshirts and stuff, soggy, wet sweatshirts. Another way you can think about this that I like to think about it is right here. Let's say your car is stuck in the mud. So we're looking at a top view of the car, okay? And there's a tree right here. Okay, so let's say that's the trunk of a tree. You could take a rope, come out here, and you could wrap it around the tree. Instead of pulling on the rope, right, you could put all of your weight into the rope and maybe get 200 pounds of force. What if you instead push sideways on the rope? If you push sideways on the rope, you're getting the same kind of thing where we see if you push this way on the rope, you're going to get the component of the rope is going to be the same as your weight, but then notice the horizontal component of the rope is going to be massive. So you could actually get a tremendous amount of force on your car by pushing sideways on the rope. Now the trick here is well, there's a couple of tricks. Number one, don't just tie it to your bumper or you rip the bumper off your car. Number two, this rope has to be extremely tight. Otherwise, when you push sideways, you're just picking up the slack. Number three, when you do this, you're only going to push, like, let's say you push this way 5 feet. Well, the car might only move 1 foot, right? And so you're going to have to take it off and then retie it and then take it off and then retie it. But eventually you can get your car stuck out of your mud with only your own body weight by pushing sideways on this rope. Another example, even though this isn't very good, imagine you have some teeth. Now, this might not look like teeth, but I'm trying to draw teeth as viewed from above. So this is like your smile is viewed from above. So You're looking in there, right? So imagine these are your teeth, and you want to put some braces on these teeth. You have a bracket here, a bracket here, and a bracket here, and then, well, there's brackets all the way along. Now you're going to run a wire through these brackets like that. And now think about this. Let's say this is the tooth that you want to move. Okay, things are a little bit out of alignment. You need to move this tooth. Well, let's just zoom in on that one particular tooth. There's a tension this way and a tension that way from the wire. Notice you get this force right here. You need an incredible amount of tension on the wire if you're going to produce a significant amount. Oh, that's right in the glare. Sorry. You need a significant amount of tension in the wire just to get a significant force on the tooth, pushing it into alignment. And then as soon as it moves, well, you got to go back to the orthodontist and they got to work on it again and keep changing the tension in the wire, because as it moves, the tension goes down. And so, that's why it hurts to have braces, right? They've got a tremendous amount of tension on this thing. And that's why these brackets pop off all the time. So let's call